Right now, modern cosmology is stuck on a single, stubborn discrepancy. When we measure the expansion of the local universe, it is moving faster than our models of the early universe predict it should be. On one side, we have the early universe camp. By mapping the cosmic microwave background, the residual heat from the early plasma, and applying our standard model, they calculate a Hubble constant of roughly 67 kilometers per second per megaparsec. On the other side, we have the late universe camp. They build a local distance ladder using standard candles, like flashing Cepheid variables and exploding supernovae. Their measurements yield a significantly faster expansion rate, hovering around 73. The gap between 67 and 73 is statistically severe. The usual instinct in theoretical physics is to bridge that gap by injecting new substances into the equations, like early dark energy, to force the models to align. But an alternative framework, known as Changism, proposes that the discrepancy originates in a systematic bookkeeping error in how we track time across a structured cosmos. Before we rewrite the fundamental laws of physics, we need to interrogate the baseline assumption that allows us to compare these two numbers in the first place: the belief that the early universe and the late universe are operating on the exact same cosmic clock. To understand the error, we have to define what time actually is in relativity. Physics treats time strictly as an operational ledger. It is the output of physical mechanisms, a sequence of recorded events, ticks, and counts. Standard cosmological practice takes localized records, like the specific arrival times and frequencies of supernova flashes, and compresses them into a single global parameter to describe the expansion of the entire universe. That compression relies on a massive assumption. It assumes that the local environments where we find our calibrators are perfectly representative of the universal average. Moving data from a specific local environment to a universal model requires a process called calibration transport. This is the rigorous tracking of how clock histories differ when moving from a dense, highly structured region into a coarse-grained universal background. If you ignore that transport process, you risk pulling data calibrated on one specific clock rate and dropping it directly into an equation that assumes a completely different one. The 9% gap between 67 and 73 points to the possibility that the Hubble tension is a mathematical bias caused by failing to properly transport our calibrations across different spatial environments. The foundation of general relativity is that proper time is path-dependent. It is local to a specific world line. Two clocks taking different paths through different gravitational environments will accumulate different tick totals. In the early universe, before recombination, the plasma was incredibly smooth. A single universal clock worked. But as the universe expanded, it dynamically segregated into a complex, uneven web. This segregation created two entirely distinct cosmic environments. The first are voids. These are massive, underdense regions that evacuate over billions of years. Voids make up the vast majority of the universe's total volume. The second environment consists of walls. These are the dense, virialized structures, the galaxies, groups, and clusters, where matter has collapsed and bound together. This structural divide creates a massive sampling asymmetry. The overwhelming majority of the universe's volume is locked in voids, but 100% of our standard candles and observational calibrators are trapped inside walls. Because observers belong to specific environments, the accumulation of their proper time follows their local geometry. A clock inside a wall has a different historical ledger than a theoretical clock sitting in the middle of an expanding void. When we measure the local Hubble constant, we are looking through the universe using wall clocks, but we are using those records to infer a void-dominated volume average geometry. We can formalize this with two specific observer families. On the left, we have wall observers, using proper time tau w. On the right, we have domain average observers, representing the coarse-grained volume of the universe, using proper time tau d. The ratio between these two rates is the tempo ratio, denoted by alpha. It is the coarse-grained rate at which wall proper time accumulates relative to domain average proper time. When an observer in a galaxy calculates the local expansion rate, they are effectively differentiating the scale factor with respect to their local wall proper time, tau w. But the theoretical background model expands according to the domain average proper time, tau d. apply the chain rule to link them, and the bias is exposed. The inferred Hubble constant measured by the wall observer equals 1 over alpha times the true domain average expansion rate. To fully explain the 8% gap between our early and late universe measurements, the present-day tempo ratio must sit at roughly 0.93. That is a 7% deviation. This cannot be explained by local Newtonian weak field time dilation. The gravity of a single galaxy only shifts clock rates by roughly 1 part in a million. Cumulative regional histories produce a macroscopic distortion that appears in our equations as an expansion discrepancy. A framework like this is only scientifically useful if it is falsifiable. If the tempo hypothesis is correct, it must produce observable, predictable patterns in late-time data. We can test this directly using tomography. We split the existing dataset of Type 1a supernovae based entirely on the physical environments their light passes through. We classify each line of sight using a strict environment proxy, such as the total void fraction or the weak lensing convergence along that specific path. The prediction is rigid. If we are failing to transport calibrations across environments, then void-dominated lines of sight must yield systematically higher inferred Hubble values than wall-dominated lines of sight. We can run an alternate version of this test by executing a host-environment split, directly comparing the inferred distances of supernovae located in underdense host galaxies against those in overdense host galaxies. To confirm the results, we cross-check the data against standard sirens, gravitational-wave events. Because sirens rely on entirely different astrophysics, finding the exact same environment-dependent drift in their data proves the bias is structural, not a quirk of supernovae. This establishes a clear null result commitment. If we split the environments, control for known astrophysics, and find 0 reproducible trends, the tempo hypothesis is bounded to irrelevance. The model dies. The ultimate test is redshift-drift. Using upcoming facilities like the extremely large telescope, we can measure the direct change in a source's spectral shift over a decade. It is a pure clock-forward measurement, completely free of the luminosity distance ladder. The tempo framework predicts that the measured velocity drift will consistently diverge from the standard homogeneous background prediction, and that the divergence will scale perfectly with the void-to-wall ratio of the local line of sight. This brings us back to the core operational discipline. Time in physics is nothing more than a ledger of predictable records accumulated within our specific, structured patch of the universe. If time requires a physical ledger of counts and states, we cannot blindly extrapolate a global time parameter through a classical initial singularity. Our model only holds authority where there are stable records to compare. This operational discipline defines the beginning of our patch as the earliest boundary where our models generate predictive records. Beyond the hot plasma phase, the ledger lacks the stable correlations required for a reliable clock history. By strictly adhering to the records that clocks actually measure, we identify the geometric biases inflating the Hubble tension. And by demanding that time be measurable, we free cosmology to explore global architectures far beyond a singular genesis.